Good day, everyone. My name is Fang from Xuzhou University of Technology. I'm really honored to have this opportunity standing here to have my presentation for my paper. And you are welcome to communicate with me by email shown on the screen. My paper is named Characteristics and Application of Cascode Gallium Nitride HEMT, and it consists of 4 parts. First of all is introduction. In this part, I will explain the reason for what I do this research and what we can do for the industrial area. In the second part, I will show you the characteristics and analysis of Cascode's gallium nitride HEMT, and the advantages of this device are explained theoretically. And in the third part, the experimental verification is accomplished. At last, the conclusion is given, with theoretical analysis and test results. So let's start. As an outstanding representative of the third generation of wide bandgap semiconductor devices, Cascode Gallium Nitride HEMT, which stands for High Electron Mobility Transistor, utilizes a cascode structure to achieve the normally off nature of GaN devices with unmatched steady states and dynamic performance of silicon-based devices. In order to promote its replacement of silicon devices and give full play to the performance advantages of Cascode GaN HEMT, in this paper, its characteristics and application is studied in hard switching and soft switching states. The performance comparison of devices is shown in Figure 1. It can be seen that the quality factor and FOM, which stands for finger of merit, of GaN devices are almost only 1/10 to 1/5 of that for silicon MOSFETs, and the performance gap becomes more and more evident with the increase of current. The results show that Cascode GaN HEMT have better performance than silicon MOSFETs, and the higher the power level is, the more pronounced the advantages is. In Cascode structure, the turn on and turn off of depletion GaN HEMT is controlled by low voltage silicon MOSFETs of gate and source. The overall threshold of the apparatus mainly depends on the low voltage silicon MOSFETs of gate source of GaN HEMT, while the threshold voltage of low voltage silicon MOSFETs is lower than that of high voltage silicon MOSFETs. Therefore, the threshold voltage of Cascode GaN HEMT is lower than that of silicon MOSFETs with the same voltage level, and the gate and source voltage have a stronger amplification ability to drain current. It can be seen that the gate charge of gallium nitride devices is much less than that of silicon MOSFETs. Significantly, the Miller platform charge QGD is only 1/5 of it. It ensures faster driving speeds, shorter switching time, and less loss of gallium nitride devices under the same driving conditions. According to the common gate and common source structure of Cascode's gallium nitride HEMT, its different working modes are analyzed. In order to study its working principles on the different working modes, the equivalent circuit model of Cascode gallium nitride HEMT is given in Figure 4. And forward and reverse conduction modes of the Cascode gallium nitride HEMT are analyzed as shown in Figure 5 and Figure 6. In order to verify the accuracy of the analytical model derived in this paper, the mathematical calculation software is used to solve the above analytical model of the switching process, and the voltage and current waveforms of the turn-on and turn-off process are made. The dual-pulse test platform is built and compared with the model results. The dual-pulse test platform is shown in Figure 7. And Figure 8 shows the experimental waveforms and switching processes. Waveforms 1 ID is 10 amps. The advantages of different attributes of Cascode type gallium nitride HEMT are explained. The reverse conduction voltage of Cascode type gallium nitride HEMT is slightly higher, and the size of common mode capacitors should be paid attention to in driver selection. Finally, the different operation modes of Cascode gallium nitride HEMT are analyzed in order to clarify the mechanism of the influence of various parameters on the switching process and obtain more accurate switching loss. An analytical model of Cascode type gallium nitride HEMT switching process is established in this paper by reasonable segmenting and simplifying the switching process and considering the influence of reverse recovery of the complementary transistor. A dual-pulse test platform is built to verify the accuracy of this model. It confirmed that the voltage and the current waveforms in the switching process are more consistent with the measured waveforms, and the switching loss is more accurate. Thank you very much for watching my presentation, and don't be hesitant to contact with me by email. I'm very glad to contact with you. Thank you. Goodbye.